everyone, today we're going to present on this topic, acid and base catalysis. The group members are Chloe, myself, Wan Ching, and Pui Wing. So this is the content of our presentation. Now let's start with introduction. Catalysis is a process that are commonly used in the chemical industry. It is a process that can increase the rate of reaction by adding a substance called catalyst. These are the characteristics of a catalyst. A catalyst does not initiate the chemical reaction. It is not consumed in the reaction. It will react with reactants to form intermediate and facilitate the formation of products. After the formation of products, it can be regenerated to react with other reactants. The function of catalyst is to provide an alternative pathway with a lower activation energy. The catalysts are used to break or rebuild chemical bonds, promoting molecules to react and increase the efficiency of the whole process. Acid and base catalysis. The chemical reaction is catalyzed by acid and base. There are three types of catalytic reaction, which are acid catalysis, base catalysis, acid and base catalysis. Acid and base catalysis can be divided into specific and general. For specific, the active species is H3O+ and OH-, while for general, the active species is undissociated acid or base. Acid and base catalysis is often used as homogeneous catalyst. The catalyst will occupy the same phase as the reaction mixture. It allows better interaction between catalyst and reactant molecules. Normally, it involves aqueous phase catalyst into an aqueous solution of reactants.
I am Wan Ching. I would like to discuss the mechanism of acid and base catalysis. The mechanism of acid and base catalysis can be explained in terms of Bronsted-Lowry theory and Lewis theory. For Bronsted-Lowry theory, also called proton theory of acid and bases, according to this theory, any compound that can transfer a proton to any other compound is an acid, and the compound accepts the proton is a base. A base, called conjugate base of an acid, is formed when an acidic substance loses a proton. An acid, called conjugate acid of base, is formed when a basic substance gains a proton. There's an initial transfer of protons from an acidic catalyst to the reactant or from the reactant to the basic catalyst. This diagram shows Bronsted-Lowry acid-base reaction. For Lewis theory, according to this theory, a species that accepts an electron pair is called Lewis acid, while a species that donates an electron pair is called Lewis base. Lewis acid is an electrophile and Lewis base is a nucleophile. The reaction of a Lewis acid and a Lewis base will produce a coordinate covalent bond in the product. In the acid-base catalysis, the reaction involves the sharing of an electron pair donated by a base catalyst or accepted by an acid catalyst. This diagram shows the Lewis acid-base reaction. There are 6 types of acid and base catalysis. The first type, specific acid catalysis. This process involves a hydronium ion to accelerate the reaction rate. It is determined only by the pH of the system, but not the concentrations of different acids. Reactant is in a fast equilibrium with its conjugate acid, which proceeds slowly to form reaction product. The slow step is the rate determining step. And the second type is the general acid catalysis. Uncharged acids or cationic acids are used in this catalytic process. The reaction rate increases with increasing buffer concentration at a constant pH and ionic strength. Proton transfer is the rate determining step. The protonated subscript reacts rapidly to form reaction product. And the third type is the specific base catalysis. A hydroxyl ion is involved in the catalytic process by removing the proton from the reactant. The proton is completely removed from the reactant before the rate determining step. The rate of the reaction depends on the pH of the system but not the buffer concentration. The fourth type is general base catalysis. Uncharged bases or anionic base are used in this catalytic process. Proton is removed during the slow step of the reaction before forming the product. It must be the buffer catalyzes the reaction as the pH is constant. The fifth type is the specific acid and base catalysis. Proton transfers involving protons and hydroxyl ions from the water. This takes place when proton transfer between intermediate and water is faster than intermediate breakdown. And the last type is the general acid and base catalysis. This type of catalytic process is involved in a majority of enzymatic reactions. An acidic or basic residue at the active site is used to facilitate the proton transfers in enzyme-mediated catalysis. This takes place when proton transfer with water is lower than the intermediate breakdown.
Hi, I'm Yap Pui Wing. I will talk about application of acid and base catalyst. Here are the examples for each type of catalyst. Specific acid catalyst in decomposition of triacyltricins. This paper showed that triacyltricins follow specific acid catalyst decomposition kinetics. The present study involved the decomposition of tricins 1 to 4. Here are the results. pH depends on the rate of decomposition of triazines. The rate of decomposition of tricin 1 was studied over the pH range of 10.4 to 12. Figure 1 shows first order reaction. The reaction rate was inversely proportional to pH. The reaction was acid catalyzed in spite of the alkaline pH range used. Below pH 10, the reaction was too rapid for convenient measurement. Table 2 shows the rate of decompositions of triazines 2, 3, and 4. 3 was completely stable under the conditions where the alkyl triazines decompose rapidly, hence it requires strongly acidic conditions. Dependence of the rate of decomposition of triazine 1 on buffer concentration. It is a diagnostic tool for detection of general acid catalyst. Triazine 1 was decomposed at pH 10.8 in CAPS buffer ranging in concentration from 0.01 m to 0.25 m. Graph in figure 2 show a negative slope. Slightly buffer concentration variations were not significant. Rate of decomposition as a function of buffer pKa. In general, the acid catalyzed decompositions have an observed risk constant of the form shown below. The summation applies to the various possible general acid species, but when the reaction is catalyzed only by hydronium ions, which is the specific acid, the summation term vanishes. This situation demands that the rate constant for the reaction at constant pH be independent of the concentration and identity of the general acids. The decomposition of 1 and 2 show no significant variation in the rate constant. This data supported the notion that the reaction is catalyzed by specific acid. The invariance of rate constant indicated that buffer species are not involved in the decomposition reaction. The reaction is catalyzed by specific ion. Conclusion: triacyltriazines decomposition are consistent with the following equation. General acid catalysis of formation of semicarbazole. Several investigations have established that the reaction is subject to general acid catalysis. At neutral pH, the acid catalyzed dehydration is the rate determining step, whereas at lower pH, the rate determining step undergoes a transition to rate determining semicarbazole attack. Attack on the carbonyl-carbon atom obeys the rate law of equation 3. The results provided evidence which are the second order rate constants for semicarbazole formation were plotted against pH in figure 3. The attack of semicarbazole showed both a solvent-catalyzed reaction predominant between pH 4 and 5 and an acid-catalyzed reaction predominant below pH 3. The observed general acid catalysis had transition states 1, 2, 3, and 4 and were shown below. Only transition states 1 and 2 evolved through general acid catalysis. Another evidence is the second order rate constants for acetone phenol semicarbazole formation is increased linearly with increasing concentrations of propionic acid at first, then level off and eventually became essentially independent of the catalyst concentration shown in figure 4. Specific base catalysis of formation of electron. Several works has established electrons as essential intermediates in the racemization of many peptide activated species. The works clearly stated the dependence of electron formation on the presence of base. It presented evidence supporting the presence of equilibrated amide anions as the reactive intermediates, leading to electron formation from 4 peptide activated esters. Below show the 4 types of esters used. Table 3 presents first order rate constants observed. The data show the observed linear dependence of rate on amine. Amine salts ratio were the most easily interpreted as requiring the intermediacy of a conjugate base of Ia. Below show the scheme which consistent with the results and show it was a specific base catalysis. By comparing the value of K in 1 with the rates of reaction with an external amine, it showed a surprisingly good correlation despite considerable variation of reactivity and structure. General base catalysis of ester hydrolysis. The paper studied the hydrolysis catalysis of alkyl and aryl esters by buffer bases. Formic esters were chosen for examination because they could undergo hydrolysis at an easily measurable rate at neutral pH and ordinary temperature. The results are hydrolysis of formic esters follow the rate law of equation below. Figure 5 shows observed first order rate constants increase linearly with increasing buffer concentration. The positive slope indicated general base catalysis. Catalysis by acetate anion exhibited an increase in the solvent deuterium isotope effect. This increase confirmed a change in mechanism from nucleophilic to general base catalysis. The solvent deuterium isotope effect and the small values of beta supported the mechanism of general base catalysis. 6 kinetically equivalent mechanisms for general base catalysis of the hydrolysis of alkyl formics proceed through transition states 1 to 6. There were 2 fully consistent mechanisms. The changes in structure reactivity coefficients indicated that as the less basic of the catalyst, the more bond formation to the attacking water molecule and the more weakening of the bond to the leaving group in the transition state. The general base catalysis of the hydrolysis of methyl formic occurred by rate determining removal of a proton from the attacking water molecule was concluded according to mechanism 2. Specific acid and base catalysis of esters hydrolysis. Acid catalyzed ester hydrolysis. The specific is catalyzed by dilute acid and the ester is heated under reflux with a dilute acid such as dilute HCl or dilute H2SO4. For example, ethyl ethanoate is heated under reflux with a dilute acid. The ester reacts with the water present to produce ethanoic acid and ethanol. Dilute acid provides both the acid catalyst and the water. In the first step, the ester takes a proton from the hydrosonium ion. The proton attaches to one of the lone pairs on the oxygen which is double bonded to the carbon. The proton transfer causes oxygen positively charged. Then, the positive charge on the carbon atom is attacked by one of the lone pairs on the oxygen of a water molecule. Next, a proton transfers from the bottom oxygen atom to one of the others. Eventually, it will join to the oxygen with the ethyl group attached. Then, an ethanol molecule is lost from the ion. Finally, the hydrogen reacts with water to be removed from the oxygen. Ethanoic acid and the hydrosonium ion catalysts are regenerated. The reaction is reversible. For the base catalyzed ester hydrolysis, ester is heated under reflux with a dilute alkali such as NaOH solution. The advantages of base catalysis over the acid catalyst are the reactions are irreversible and the products are easier to be separated. Alkali hydrolysis of esters is also called as saponification. The general steps are: Step 1. The hydroxide nucleophiles attacks at the electrophilic carbon of the ester CO double bond, breaking the pi bond and creating the tetrahedral intermediate. The intermediate deforms, reforming the CO double bond, results in the loss of the leaving group, the alkoxide, producing carboxylic acid. And the final step, a very rapid equilibrium where the alkoxide functions as a base deprotonating the carboxylic acid. General acid-base catalysis of the reversible addition of bisulfite to 1,3-dimethylurate. The reaction was kinetically determined to see whether or not the catalytic behavior of the system can be used to explain modes of catalysis by pyrimidine alkylating enzymes. The results are: the desulfonation follows strict first-order kinetics in every reaction as a mean. Semi-logarithm plots of A infinity minus A against time were linear for at least 3 and in most cases 5 half-life. Figure 6 shows the results of a typical experiment with ethanolamine buffers. The absence of isotope effect at carbon 5 in measurement of rates in deuterium oxide supported the buffer catalysis data, indicated that the mechanism involving general catalysis of proton transfer. In desulfonation reaction, hydroxide ion was the only base catalyst tested which has negative charge. Proton extraction by hydroxide ion caused transition state 1 had additional negative charge, hence might have less stability than would be expected in the transition state 2. The data presented for the general base catalysis were consistent with 3 kinetically indistinguishable mechanisms, all of which involve the expulsion of sulfide ion via simple carbon-sulfur bond cleavage, shown in equation 3 to 5. The mechanism in equation 5 indicated that in both directions, the reaction involved either rate determining proton extraction or proton donation to a carbonyl intermediate via general catalysis. The paper also indicated that general acid catalyst proton donation to carbon 5 concomitant with nucleophilic attack of sulfide ion on carbon 6 of the pyrimidine ring system could occur.
In conclusion, acid and base are useful catalysts in the production of various chemical compounds. Acid and base are commonly used as homogeneous catalysts and they can speed up reactions by affecting bond polarization. In specific acid or base catalysis, only the H+ or OH- accelerates the rate of reaction, which the rate of reaction is dependent on the pH only. In general acid or base catalysis, molecules apart from water will act as a proton donor or acceptor. The charges in the transition state is stabilized and the rate of reaction is dependent on the buffer concentration. These are the reference for our presentation. Thank you.